practice or additional load. So you already know everything you will do until the end of semester. Hi, Mahek. Nice seeing you connected.
Hello.
How are you?
Yep, good.
Okay, let's see.
Usually I stay at home basically. You don't go to the campus.
Correct. I don't know what to do at campus. It's maybe just a little different and different desk and different screen, but all effort are online, and we have group meetings with students from the group in the online fashion, and computation.
Yeah, ultimately for the computational group, it's okay to work from the home.
Right. It's not a big difference. Hi, Johan. Nice seeing you connected. How are you?
Good, how are you?
Doing good, thank you. So we are missing Raju. And Yang Chao. We are waiting them to connect. Okay, probably since it's time, I'll start, and let's hope that they will. Oh, hi Raju, hi Yang Chao. We were waiting for you and happy to see you connected.
Hello.
Okay, so thank you for your dedication to the course. We are very close to completion. So let me share the plans, and I'll probably start with slides right away. So in the remaining time of the course, so here is this little highlight tool is where we are now. So the academic goal for today's meeting is to get up to flowchart for TDDFT theory. And before we go to it, I will review suggested effort towards your projects. And right now we are doing a little overview of the remaining parts in the course. So there will be two forms of reporting for the project. One is the paper written report, which will be due in 1 week from now. I understand that it is very short time, but it will be short paper. So whatever you collect, generate data and collect during this weekend and maybe next lab, please try to squeeze it into Word document and send it as an email before start of the class next Thursday, and we will practice collective academic review. I promise you will like this activity, and you may ask Steven how it goes, because he was attending similar class in the last semester. On the coming Tuesday, I will bring a little bit more suggestions on how to organize data that will be available into form of this written report or paper. And by votes and elections last week, we agreed that the presentations will be in 2 weeks from now. On Thursday, May 14th. So before the presentations, there will be chance to maybe improve materials provided in the written reports. So today, I hope there will be the last academic part, last meeting on the academic materials, and next week we will be focusing only on the activity related to the research. So during when I was sending you the materials for the lab number 14 yesterday, I have included additional optional material on the next level theory that I am not going to cover in the class. We just physically do not have time. So it was a group meeting presentation of one of the students, but it is a really good overview, like next step, what can be done in addition to what we cover in the class. So by votes, we agreed to make a presentation on 11 a.m. on Thursday, May 14th. And everyone has models for individual research. The common motive for exploring, for making this research is to prepare 2 sets of geometries, one optimized and one perturbed by high temperature molecular dynamics, and compute spectra, density of states and orbitals, and compare. So how much the perturbation of the geometry by heating affects the electronic properties of the materials. So I understand very much that you are doing an heroic feat, and typically for the graduate school research or thesis research, people invest years, and here we are squeezing it into 1 week. So it will be small amount of materials, and it is very understandable. So just try whatever is possible in a given time. There, supposedly, everyone submits jobs, getting results, getting figures. Then the next question is how to organize this data and how to analyze, report, present in a reasonable way. So depending on the specifics of the system, one can explore different anions, cations, model in ground state or thermalized, and there are several properties. So I'm going to share some informal comments how this organization can be done, and then offer a suggested schedule of figures that how they can be organized, and this schedule of figures is arranged in a form of a homework, but it is only an auxiliary step towards completing your research projects. So this is one of the papers generated out of the in-class project, and here are the ways how the density of states for ground excited ground, this one is excited, here is cation models, how the density of states is changing. just an idea so that one can arrange multiple individual images into a super figure with multiple panels. A little note, which this one is probably most appropriate for Zhaofan. If the model, and maybe for Rebecca, if the model is composed as a combination of two parts, for example, carbon nanotube and adsorbate, or graphene hole and gold particle, or gold particle and H2S, or in the project by Steven, metal-organic complex and adsorbed water. There is a chance to look onto total energy of the composite system and then individual energy of components. And comparing these total energies, one can assess so-called binding energies. So here is the list of possible configurations. So everything I'm showing, it's a little bit extra because the minimal set of data is just equilibrium geometry and geometry perturbed by heating, and then comparing density of states, spectra, and orbitals. But for some models, one may volunteer to also explore not only the ground state neutral model, but also create it in the anionic or cationic state, to prepare it in the excited state by Fermi weight, and explore different spin multiplicity like singlet, doublet, and triplet. Singlet, doublet, and triplet, it is related to what Salim is doing. I see that he's not on the online connection, but for him, he's actually already doing these calculations, spin flip, changing the spin multiplicity. So binding energies. So if one has a composite model and then standalone models, one can subtract these total energies and get binding energy. It is one of the simplest things that can be compared to experiment, and there are natural ways to find the value of binding energy for almost any realistic system in the literature, or get interaction with experimentalists and ask them to do it. It's a very quick, simple experiment. If one does have a curiosity, one can compare density of states of the composite system and standalone systems. If there is no binding, if systems A and B do not form chemical bonds and connection, then density of states of one system and another is just an arithmetic sum. The peaks just superimpose. But if there is a chemical bond, then there are additional peaks or disappearance of some peaks. So it's by comparing density of states of individual models and composite model, one can get measure of interaction between systems. Same works with the spectra. Like if spectrum of composite model is just a summation of individual elements, it means they do not interact. So this comment can be important for Raju. So suppose I am exploring a model by setting up different sequence of directories with different temperature of heating, and then after each heating, like 100, 200, 1000, 2000, 3000 Kelvin, and after each heating I run molecular dynamics. So if it is not possible to do everything, we are very limited in time. I'm just overviewing potential opportunities. So if the temperature is low, then electronic structure, like density of states, orbital spectra, after molecular dynamics will be practically the same as before dynamics, because there are activation barriers for phase transitions, for chemical reactions, and there are critical values. So, but if the temperature of molecular dynamics will be above specific activation energy, which is different for any specific system, then system will start decompose, transform, and experience drastic changes. So one of the arrangements of computational research can be formulated as an effort to find an activation energy, and it is achieved by repeating same style molecular dynamics at different temperatures and see at which temperature drastical changes appear. So activation energy is a standard concept in chemistry. There are special ways to treat it, like transition state theory, Arrhenius law, and any effort in this direction is very easy to lay along these concepts of Arrhenius law. Okay, more comments. For molecular dynamics, we all are using the thermal heating, but this is not, and you are aware from the last presentations on VASP skills that upon completion of the heating procedure, the cont car accumulates additional segments. So top portion includes coordinates and lower portion includes momentum. And if it is thermal heating, then momentum will be random by value and direction. As an alternative way, one can set up a manual preparation of the momenta. So one can set up all momenta equals 0 and then manually select a line that corresponds to a specific atom and assign momentum, for example, so that a specific atom or group of atoms collides and approaches substrate. So one can put this projections of momentum x, y, and z equal to a specific value. And then instead of random thermal motion, one can set up that one molecule approaches a group of other molecules and set up collision experiment. This year, I do not see choices related to this setup, but it can be done by Steven to make like water molecule approach and collide with ruthenium ion. It can be done by Mahek for H2O2 molecule colliding in this lipid. And it can be done by Zhao Fan for adsorbate for this aniline molecule heating the carbon nanotube. So on one hand, we are limited by time. We cannot do too many things. On the other hand, if I am getting excited in a project like this, and there are computational resources, the amount of computed data, figures, and tables can ramp drastically. And then, if you do not feel it, you're lucky. But if you would set a little longer time, then one can swamp in the sea of this computed materials. And then there is a big challenge how to organize and review them in a logical way. So one of the reasonable arrangement is to report geometry, total energy, gap, binding energy, density of state, spectra, orbitals, maybe follow temperature as function of time, and this could be a set of tables and figures for the paper. I know that if I would listen to it, I would probably feel, on the side of being student in this class, I would feel a little irritation that too much things are demanded. But nothing is demanded. It's only a suggestion. It is a suggestion in case you feel lost and you do not know how to organize data. So let's make it a little bit more formal. So it is suggested. It is suggested organization. So in case you are running several calculations and we all are planning to report results of this research in the form of written report, then there is a standard practice in arranging and organizing research papers as a set of observed materials, which is can be presented as set of data in tables, but better for human perception, it is arranged as figures. And let me, I will quickly jump to the slide number 2, and repeat the goals of the course. So the goals of the course is to get over the theory background, practical skills of computation, and then scientific communication. So to look for computed observables and assess possibility to compare them with experiment. So in the next week we are, and in the presentations, we are moving to scientific communication. So how to communicate the computed results. So, if available, if you are successful in generating a lot of data, you may try to categorize this data and arrange them as this set of figures, and prepare a template in Microsoft Word and copy paste their figures. By standards in scientific literature, figures are labeled by numbers in increasing order, and figures are typically accompanied by the captions, basically typing one sentence what is shown in the figure. And possible arrangement is like, first figure is geometry of system, explaining what it is, table showing total energies or maybe gap values for if there is more than one model. Figure 2 can be density of states. This one is optional if one explores different number of electrons, as Steven is doing, or different spin configurations, as Salim is doing. It could be another figure. And let me bring an example of such figure that Salim has prepared. So he has prepared the density of states for his model, and then for each peak he makes an insert showing how the orbital is looking. So it is a good multi-panel figure. So next could be a figure with optical absorption for pairs of orbitals, and as you have seen in the example from Salim, one can combined together density of states and orbitals. So also let me quickly share a criterion of choosing the orbitals to show. We all know how to fabricate a lot of files for orbitals and we know how to visualize them with VMD, but how do we know which orbitals are most important for scientific intuition for analysis? So possible criteria are those orbitals that seem to be contributing to optical absorption, or those orbitals that seem to contribute to charge transfer. Or if these criteria do not match, then just HOMO and LUMO. So movies are the best way to represent molecular dynamics. But if the reporting document is just a paper, it's still a little challenge to include movies into papers by today, and therefore there is a way to just show several snapshots of molecular dynamics, especially if there are some chemical transformations. So supposing I have 1,000 steps of molecular dynamics, and at time step maybe 300 and 350 femtoseconds, I have a group of molecules migrating. So I'm showing first, last, and couple of snapshots in between, showing just pathway of the reaction. And this is how total energy depends on time, which I think it is also optional to include. So what I suggest to accomplish during the weekend and share by the time of next meeting is prepare this set of figures as a Word file. Please do not worry if some data are not computed or not available. Just share what will be ready by Tuesday morning, and this effort is needed in order to complete the project in the limited time. So later on you will be able to add more materials, but if we start thinking on how to organize computed data, it will help tremendously and remove stress from last meeting, or it will spread effort over a longer time so that we do not feel major stress. So let me check if there are any questions related to the procedure, to these suggestions. Are there big protests or anger or irritation or constructive suggestions about this procedure? So since there are no protests, it means everyone supports this plan. No one wants to object, or yes? Please repeat once again, slower.
What is the command to find the total energy from the output?
Oh, okay. Yep. Yeah. Raju is asking how to find total energy of as function of time. So this command, we were doing it while exploring the heating process, and then after one does this command, one can forward it into file TT, and then the column number 3 will be temperature, and column number 7 I think will be kinetic energy. Like number 5 will be total energy, number 7 kinetic, and number 9 will be potential energy. So along the trajectory. Does it make sense?
Yes, thank you.
Okay, thank you. So we are done with part related to research, and let's go to academic part. So last time we compared orbital picture and excitonic picture, and in the excitonic, both orbital and excitonic picture, one can compute the absorption spectra. And for obtaining an absorption spectra, one needs to get this transition energies and oscillator strengths. So in today's meeting, we do have two expected results. One, that I would make one more lab if semester would be longer, but it is very, very simple calculation. So if one returns back into Gaussian and runs a Gaussian job with additional settings, additional keyword added into the .com file, then Gaussian will intentionally compute the spectra. So one needs to set TD, which tells that it will be TDDFT calculation. Then if one is not going into any modified spin multiplicity, one writes singlets, and then one needs to set up number of states and root, which means how many excited states are computed, how long this index will run. And here is an example of absorption spectra for one of the molecules that we were practicing before we went into VASP. So absorption spectrum of titanium hydroxide with gap above 3 electron volts and several absorption peaks. So it is one outcome of today's meeting that I will go step by step with details. And another outcome, we are going to overview the flow chart of how the time-dependent density functional theory is working. So we will overview equations of TDDFT theory once again, and then try to collectively, maybe one person at a time, to fill these boxes in a flow chart. So we have seen these equations before, like Cassida equation, and since we are speaking about pairs of orbitals, it is a second functional derivative instead of first one for the coefficients of this equation. So we are starting lecture right now. The excited state theory poses a goal to find transition frequency or transition energy and transition density because it helps to obtain transition dipole by making this trace operation of transition density matrix and the dipole operator. And this transition dipole is used to compute oscillator strength. If one implements this is implemented in Gaussian 09 or Gaussian 16 software, and the keyword to not 19 is not yet available, 16 software, one adds keyword TD, singlets, and then root, so number of excited states. Note that in Gaussian you cannot, just by nature of the software, it will not work if you request like 10,000 excited states. When we do independent orbitals approximation in VASP, we can go as far as needed. In Gaussian, typically, if one is not requesting more than 100 excited states, otherwise it will be too long. So after this calculation has been requested, there is a .log file inside computed by Gaussian, and there this .log file will look differently compared to output that we are getting in the Hartree-Fock DFT. Instead of list of virtual and occupied orbitals, it will include list of excited states, and these writings are literal copy-paste from the .log file. So it will list excited states from 1 up to the number of requested excited states, and then it will show the transition energy, also converted into nanometers, and then oscillator strengths. In addition, Gaussian reports which pair of orbitals contributed to this first excited state with which proportionality coefficient. So if you look in the excited state number 1, it looks very similar to orbital picture. So transition from HOMO to LUMO gives first excited state. But if you go to the next excited state, it shows that it is contributed from both HOMO minus 1 and LUMO, and HOMO minus 1 to LUMO plus 1. So what I want to focus your attention at, that one excited state is contributed by 2 orbital pairs. So this is the main strength, main specific feature of this TDDFT approach. So if I am a simple guy who doesn't need theory details, I just need to parse transition energies, these blue lines, and oscillator strengths from these lines. And by having these 2 data sets, I can compute spectra. If I want to get a little bit deeper understanding what is going on, I can bring up this diagram that we did before, so that density is composed of density matrix for occupied, unoccupied, and transition segments, and then understand that we are looking onto this black box transition density. So for excited state 1, it will be non-zero element only for HOMO and LUMO, and the value will be this 0.69. For second excited state, it will include this HOMO minus 1 and LUMO element, and then a few others. So more and more elements of density matrix will be non-zero. What I didn't made here properly, one needs to put index of excited state everywhere. So each excited state is expanded in terms of orbital pairs. So first excited state only HOMO to LUMO. For second excited state, there are this several elements of density matrix are being non-zero and contributed. And these numbers in dashed circles, it is what are the values of transition density matrix by solving the Casida equation. So when one runs TDDFT calculations, one is obtaining transition density matrix. And if I'm picking only transition energies and oscillator strengths data, I can convert them into the absorption spectra in the same way as we do in the independent orbital approximation. So this approach, and we reached goal 1. It was one of the expected outcomes of today's meeting. If I look online for Mark Casilla, he has a web page that welcomes everyone in French, because he's in Canada and probably his first language is French. So this paper of 25 years ago is when this equation was derived. So here is his photograph, and here is his equation. So we already went through this equation in the previous lectures, but let me go over it once again, just in case if your future research will need high accuracy absorption spectra. So there is also a little puzzle that I'm willing to disclose today. So it will be a very natural question if anyone in the class asks, where is time dependence? The spectra are time independent. The results that are being computed by time-dependent density function theory are just set of transition densities, transition energies, and transition dipoles or oscillator strengths. So please let me know if you are thinking about it, if this paradox did attract your attention in while listening to it, if you did care about it. Did anyone was surprised by this paradox that we are getting static time-independent data, but the theory is called time-dependent theory? Raju?
No,
Did you consider it as a paradox or not quite?
I didn't get it.
So the time dependence means that there is some dynamics, something changing over time, right?
Yes. Yes.
And when we are describing theory for excited states, TDDFT, it gives only static information. Nothing is changing in time. So it sounds like a paradox. We call the theory a time-dependent theory, but we are computing static properties only, right?
Yes.
So I'm going to comment on this. So in fact, the starting point for the theory and for this derivation is an equation that looks very much like Kohn-Sham equation, and Stephen should be comfortable with this. So it's like time-dependent Schrödinger equation. Time derivative of wave function equals to Hamiltonian acting on the wave function. Stephen, do you support this equation? Or do you object?
Yeah.
Oh, okay, good, thank you. So this is a very standard thing in quantum mechanics and physical chemistry that everyone agrees. So now the external potential typically is contributed only by positions of ions. But here we can assume that in addition to positions of ions, there is time-dependent potential which is contributed by oscillating electric field. And then one is formulating a question: how the solution of the time-dependent equation for this wave functions will respond to this oscillating potential. Since the total potential here depends on density, one needs to construct density or change in density in terms of pairs of orbitals times some expansion coefficient. But in the transition from this second equation to the third, one is implementing Fourier transform. So one is plugging in. Let me put it here, so that everything wave function and expansion coefficients, so psi of omega and t, or not t, psi of r and t, is a Fourier transform, which is integral exponential I omega t psi of omega d omega. So if we plug in this definition into this equation, and then in the next equation we plug in the definition of this rho capital AI as function of time is also a Fourier transform. I will just skip details. Fourier transform of rho AI that depends on t. Then one would transform all equations from time domain, from oscillating things, into frequencies. And since electric field may oscillate at different frequencies, then response of the electronic density, electronic system onto field of different frequencies will be different. Okay, I hope I did answer this transition from time to frequency domain. But originally, the first equation in this concept starts from time dependence. Therefore, although the final answer doesn't have time, the theory is called time-dependent density functional theory. So those are transition densities. We are skipping diagonal part of density matrix, and the indices A and I are different. And then this, depending on whether occupied and unoccupied goes first and second, or second and first, one calls it X and Y. So those are transition density metrics. And in the community, at least the Mark Cassidy uses this uppercase rho, or Latin pi. So then one records the density matrix in form of a vector and formulates an equation for eigenstates, unknown eigen energies and unknown eigenvectors. So the matrix for this matrices that compose the superoperator will be only energy difference of basic orbitals if we neglect Coulomb interaction, or they would include this Coulomb kernels if we allow interaction between orbitals, like electrons and holes attracting each other. This K matrices, or A and B matrices, are second derivative delta 2 over delta rho squared of total energy if we are speaking on the language of total energy, or if you are speaking on the language of potential and transition density, this one often uses this form. So first derivative of potential over transition density. Here are some references if you ever need to make computation and explain what you are doing. Okay. Those are conversion from matrix to vector that we already did. And now it is time to convert this last theory in our class into the language of flowcharts, so that we do not need to be programmers, but by graduating this class, we should be able to be directors of programmers, to give basic ideas that to be implemented in computation. So in this TDDFT, we do have several components. We do have input information, which are positions of atoms, number of electrons, total tolerance limit, and number of excited states. And we have an output of transition energies, oscillator strengths, and transition densities. And there is a Cassida equation. There is a way to compose density out of the orbitals. And let's try to arrange these components into the flowchart that would work for practical computations. So let me invite everyone to join the link that has been shared in the common chat, and watch this template in the Google Docs documents. So I do see 2 class attendees did log in. Please continue to log in for everyone.
Can you share the link again?
Pardon me? Let me.
Professor, can you share the link again? Yeah.
So I was the first one. I saw the first one basically.
Who is volunteering? Amir, are you volunteering?
Yes.
Okay, the first one has a better chances, better choices. Okay, please go ahead and move one of the blue boxes on the right into one of the. Okay, thank you, Amir.
Yeah.
Rebecca, would you like to be the second? Second one is also, you can select the easiest one. Algorithms typically begin with input and finish with output. Rebecca, are you online on the connection?
So I'm working getting to Google presentations.
So were you able to connect and see this Google Doc, Google presentation?
Yeah, I have it now. Can I place the output?
Yes, please do. Excellent. Thank you, Rebecca. So yeah, lines have moved a little bit. Maybe we need to do one undo and then it will fix it.
Wait, did it work?
No, it is correct. I just see it is slightly modified the visual presentation. Yeah, this is good. So the output goes here. So, Steven, would you like to be the next?
CHEM676 could be a good option.
Steven, are you online?
Yes, I'm here.
Okay. So, do you have any preferred box that you want to move?
I think.
I already moved the guest XY.
Oh, okay. Yeah, correct. Yeah, very good. Very good. Thank you. Thank you. Mahek, do you have any boxes that you want to move?
Yes. Can I do that? Is that okay?
Yes. Yes. Okay. Good. So we have 4 boxes and probably 3 people. Zhaofan, is there any box that you want to move?
Yeah, I want to choose the
Excellent, excellent. So I think we are. This is correct. We are practicing pattern thinking. So as in all our previous flowcharts, the diamond forking was depending on the matching the precision, the accuracy condition, so that through iterations the precision of a selected observable is smaller than tolerance limit. Yes, very correct. Yang Chao?
Yeah, sure.
Okay, very good. Raju, now you have the most complicated part. You need to select.
You can do flip-flop.
Excellent, excellent. Thank you. So after the supermatrix coefficients have been set up, one can solve for Cassida equation, and this is solved again and again until the transition frequency gets less stop changing. So one computes Cassida equation and then reset density. Out of the density one finds total energy and this A and B coefficients, solves Cassida equation and then repeats. And after one achieves the correct precision, one is getting to the new excited state for which one would solve. And after one is finished scanning through all excited states, one is converting the transition density, this x and y, which we can call rho sub I, into transition dipole and oscillator strength. And then one can go ahead with the spectra. Well, many thanks to everyone for contributing. Everyone gets full credit for this in-class quiz. and we are close to full completion of the class. Let's see if there are more slides. So we filled empty spots, and in this in this line, yeah, it is exactly what you have done. So in this computational chemistry course, we started from molecular Hamiltonian. We practiced Born-Oppenheimer separation. Then we studied Hartree-Fock theory to get the mean field concept and simplify system from many degrees of freedom, many electronic degrees of freedom, only to one set of orbitals through this procedure. Then we studied density functional theory, which is which is based on concept of exchange correlation functional, and we finished the time-dependent density functional theory, which is not in fact time-dependent in its practical computation. Through this course, we got practical components of building atomic models, optimizing geometry, finding density of states, ionization energy, and electronic affinity. We got practical skills or review how to compute spectra, and I believe everyone is skilled user of WASP for running ab initio molecular dynamics and making movies. So from now on, the remaining week will be focused only on research and application of these skills. So please accept congratulations with finishing the academic part of the course, and we are done with today's lecture. Anyone is welcome to disconnect and depart. I'll stay here to answer any questions, and we'll be looking forward to any communications by email. Done.
Thank you, Dr. Kenan. Have a good day.
Thank you, Amir. You too.
Bye.
Bye.
Dr. Dimitri,
Yes?
do we need to submit the paper by next week, Thursday?
Yes. Yes.
1 day or 2 days delays will be counted?
Pardon me?
Couple of days of delay can be counted?
Thank you for the question. Wait, Raju, I understand your question, and I want to give a very specific answer. I even can type it in the common chat. So the first draft of the paper is strictly due next Thursday. But after next Thursday, you will have a chance to update for the final draft for another weekend. So final version is due on Monday, whatever will be 14, 13, 12, 11, May 11th. But please bring the first draft in a week from now. It should be ready by next Thursday. We need it in the class. Does it make sense?
Yes, thank you.
Okay. So it's not a big secret. We will collectively review, like we will split drafts between several reviewers from the class and read works of each other and provide feedback for improving. So everyone needs to bring first draft next Thursday. Okay. Other more questions?
Thank you, Dr. Dimitri.
Thank you, Raju. Have a nice weekend. And yes?
Yeah, you too. Same to you.
Uh-huh,
Have a nice day.
thank you, thank you,
Thank you, Professor.
Bye.
Thank
Thank you.
thank you, Mahi.
Thank you. Have a good day.
Thank you, Rebecca. You too. Okay, I think everyone has disconnected. Mason, did you hear back from Daniel about availability of May 14th?
I have not yet, but I'll let you know, or I'll have him let you know whenever he gets back.
Okay. Okay, excellent, excellent. Yeah, thank you much for the all forms of support and for staying with us. It's really important, and we all feel less nervous with your backup support. Okay,
No problem.
thank you. I'm going to disconnect. Have a nice weekend and see you next week.
Yep, you too.
Thank you.